So, hello everyone and welcome to this Junior Researcher webinar. Thanks for being here today for this seminar that will focus on exploring neutron-rich and proton-less nuclei from silicon isotopes between shell closures to Tetra-Neutron resonance. And this seminar will be presented by Quentin Delignac, who is currently a postdoc at IJCLab. So, Quentin, the floor is yours.
Thank you, Lou. So hello, everybody. So firstly, I would thank to Lou and all young organizers to let me to present this work. So I will directly dig into the details. I will present the two parts of this webinar as for the silicon isotope between L=20 and L=28, which was my PhD work at LP2I Bordeaux. And as a second part, I will present the study on the Tetra-Neutron isobaric analysis state in hydrogen 4, which is in fact my work now at IJCLab. So let's start with the silicon isotope, and I will talk about the region between L=20 and L=28, where we can find these two magical numbers in neutrons. Well, we can see it directly from the strong first 2+ energy, like the calcium 40, sulfur 36, or silicon 34 at n=20, but also for calcium and sulfur at n=28. But here we can see that there is one that is going downer than other. In fact, yes, silicon 42 is not anymore magic, and it was found that that's with a strong oblate deformation. So how can we explain this loss of magicity of the silicon 42? And in fact, Takao Otsuka started in the beginning of the 2000 years to explain it by a strong monopolar part, which is the tensor force. So in the silicon 42, the tensor force is explained basically by the number of neutrons and protons that are in specific orbitals. Here, for the silicon 42, in the T3 protons orbital, we don't have any protons. That implies some interactions on the neutron orbital, where the neutron F7 and F5 will be compressed and in the benefit of a loss and a reduction of the gap n=28. But also, we see that the F7 neutron orbital is entirely full and will imply some compression on the D3 and D5 proton orbital, and so compress the Z=14 protons gap. So these both reductions allow more excitation in the proton SD shells, but also in the neutron FP shells, and so develop more deformation for the silicon 42. Now, we know that previous studies show the evolution of shape below calcium 48, where mostly argon 46 is seen as a spherical shape, and sulfur 44 is seen as a coexistence shaped nuclei. But of course, silicon 42 is entirely deformed. Through this tensor form mechanism that we already saw that there is a reduction of Z=14 and n=28, and these both protons and neutrons play a role in the deformation of silicon 42. Now, the goal of this study was to follow the evolution of proton and neutron excitation along silicon isotopes. So how we can quantify, in fact, this proton and neutron excitation? We can use, for our case, the excitation of the first 2+ states with different probes. For example, and we will see that we can use Coulomb excitation, but it is sensitive to protons and allow to measure the BETU's values. But also we can use proton inelastic scattering, pp prime, that is, in fact, sensitive to protons and neutrons, in which we can determine and measure the differential cross-section of this reaction. Performing these both measurements, in fact, we can basically characterize another quantity, that's the ratio Mn over Np, which has the ratio in the proton and neutron matrix elements, and which characterize directly the neutron and proton excitation. Three cases can be observed with the Mn over Np ratio. In most nuclei where we have a collective vibration with the same excitation for proton and neutron, the ratio Mn over Np is standard to equal to n equal over z. In proton closed shell, of course, we can observe a stronger Mn over Np than n over z, and in neutron closed shell nuclei, we can see a lesser Mn over Np than n over z. But now, can we do both measurements with the same radioactive beam? That, in fact, we know that all radioactive beam can be complicated to produce. In fact, and yes, of course, we can do both measurements by using a brochette mode experiment. So why brochette mode experiments? In fact, I will now detail this experimental setup, and why it's because of the radioactive beam. So we use the Ganil facility cyclotron in order to create a primary beam of calcium-48 at 60 MeV parade. And we use the Lise target in order to make some fragments of this primary beam and doing a secondary and exotic or cocktail beam. Here you have the identification with the delta E time of flight identification matrix, where you can see the production of the silicon-36, but also the production of other nuclei like the sulfur-40. So one setting was performed on silicon-36 and sulfur-40, another one on the silicon-38 and sulfur-42, and sadly, no setting on silicon-40 because of major failure of Ganil cyclotron and water leaks. This is important to mention that we will use for our analysis the sulfur isotope as a benchmark for the entire analysis. So, concretely, what is brochette mode? Brochette mode is just two independent setups in series at the end of the beam line of Lise. Here you have the first setup, seeing the beam, which is ACTAR TPC, performing the measurement of the proton inelastic scattering. And for one, the analysis is still in progress by the ACTAR collaboration. Another dedicated setup was used as a Coulomb excitation setup, and it was the main subject and the main object of my PhD analysis. So I will dig into detail for the Coulomb excitation setup, where many auxiliary detectors was used to perform heavy ion detections. We already seen this identity matrices that we use directly from identification of Lise. You use also CATS tracker detector in order to reconstruct the position at the target and the incoming angle on the gold target, which is a Poulex target. And after the target, it was mandatory to determine the particle outgoing from the target. So we use a pair of DSSD in order to track the identification of the particle, but also track the position and the angle of the particle outgoing from the target. DSSD was used for what we call the big angle, and a newly developed 0-degree detection was used for the lower angle, with also an identification particle by particle and position reconstruction. Of course, this ensemble of DSSDs and ZDDs was simulated in order to reconstruct the geometrical efficiency of this setup. As gamma ray detection, we use exogam germanium, highly pure germanium detector, where you can have the intrinsic resolution and intrinsic efficiency, but also we use lanthanum bromine of Paris detector, where you have also the resolution and the efficiency. So as I already said, as benchmark for the Coulomb excitation, here I have some results for sulfur 42. Here you have the both spectra for exogamma and Paris with non-Doppler corrected, and where we can see clearly the peak of the gold, of the Coulomb excitation of the gold target, here and here for Paris. But also some other contaminants, for example, for room contaminant like potassium 40, and Paris contaminant with lanthanum gamma rays. When we perform the Doppler corrections, we can go now in the referential of the moving nucleus. And now we can see directly the 2 plus in exogamma and in Paris, the first 2 plus of the sulfur 42, but also another gamma ray of the sulfur 41 coming from the stripping of the sulfur 42 to sulfur 41. And that's implied that with no angular selections, we have a non-negligible nuclear component. That's why it was really important to make gates on angle and in order to characterize the Coulex part of the Coulex part of the reaction and the nuclear part of the reaction. So here you have the cumulative gates on angle with from 0 to 2, 3.3 or 5.5 degrees, where we can see the development of the nuclear contribution for each detector, exogamma or Paris. Here I show you, of course, the result from the most exotic nucleus that we get is this data for the silicon isotope, which is silicon 38, where we can see also the peak of the 2 plus of silicon 38, but also some nuclear component coming from the silicon 37. So this result, so this spectra was a start point for measuring new behavior, but also performing some new interpretation of the existing interaction in this region, which was SDPF UX. So about the result, we performed an absolute BE2 value determination using the code DUECO, which is a coupled channel of Coulomb excitation code. And so we determine the weighting average of gamma from exogamma and Paris and determine a fit using DUECO calculation. That leads us to a chi-square minimization, and so a central BE2 value. We did this for all the 4 nucleus that we had as benchmark and as interest nucleus, so for the sulfur isotope and for silicon isotope. And here you have the table that summarize all different results, where we can see a good agreement between literature values and this new work values. So as I said, as there is some new result, this was a good opportunity to reevaluate the interaction in these regions. This work was in collaboration with Frédéric Novaki and Duc Dao from IJCLab in Strasbourg. So here you have the result from the, how to say, not old, but previous version of SDPF, which is SDPS-U, where no mixing was authorized and where it was already really consistent with the observed values. But the most advanced interaction in the region is the SDPF-U, which can authorize mixing between SD and PF shells. And these interactions allow to characterize from n equal 20 to n equal, and it was the goal to characterize with this interaction from n equal 20 to n equal 28. So here the previous version of the SDPF-U show strong allowance to and allow too much mixing, and this new work help, in fact, to constrain a bit on the SDPF mix, where you can see with by constraining we reduce the mixing with SDPF shells, and so we reproduce better the results of our result. Of course, I have to mention the really recent result from IJCLab. Well, they performed the measurement of silicon 42 Coulomb excitation and find a 500 value for BE2s. But well, we seem to see that this value is really also coherent with our value and with new determination with the SDPF units updates. So in conclusion of this part, so we saw that we measure, in fact, simultaneously the proton inelastic scattering and the Coulomb excitation for silicon 36 and silicon 38. So of course, the inelastic scattering data are still under analysis with ACTAR collaboration. We improved the BE2's value. That's nevertheless important thing also, because it's allow us to progress in the interpretation and in the effective interactions of these regions. Of course, the same measurements was performed in IJCLab for silicon 42, where they measure one time the proton inelastic scattering and another time the Coulomb excitation. Of course, and in fact, yes, we can deduce also that this is really consistent BE2s, and that's also a signature of the reduction of the Z equal of 40 under the action of the tensor part of the interactions. That concludes the first part. So now I invite you for the second part of the Tetra-Neutron isobaric analog state, and I will introduce a bit about the context. So why proton-like system, or as say other people, neutral nuclei? Neutral nuclei are long-standing. Is a long-standing question, like 4n, 6n, 8n. And in fact, the first hint of its intervention was published in 2002. Where in this plot, we can see that some events in this reaction of the decay of the beryllium-40, some events, like 6 events, match, in fact, with the system of 4 neutrons. This start points lead to another study and another hint of the observation of the tetra-neutrons with Duer et al. Published in 2022, where with this reaction with helium-8 pp alpha, we can see a strong resonance for a system of 4 neutrons. This system by theorists and was really there is in fact still huge discrepancy between experiment and theory about the 4 neutrons, and that's why we push the hints further. And now the open question is, if well, there is 4n system, there is other maybe 4 nucleon system then can lead to same resonance. And here, if we say that what Duer et al. Saw is well a tetra-neutron with an isospin at t equal to 2, we should see in the hydrogen 4 an isobaric analog state with the same isospin t equal to 2. So now it's still the open question: is there this isobaric analog state of the tetra-neutron in hydrogen 4? So now, how can we populate these states in hydrogen 4? And one reaction is, in fact, a good probe to populate these states is the helium-6 p helium-3 with transfer reaction, where we can allow to populate T equal to 1 and T equal to 2 state in hydrogen 4. And as hydrogen 4 decay via triton, deuteron, and proton, this is a really high selective reactions. Also, by isospin symmetry, IJCLab have to decay via proton plus 3 neutrons. So now I will move to the experiment setup that we performed previously in July in Ganil on the experimental setup MUGAST at least. So we used the primary beam of carbon 13 at 50 MeV per U, and fragmented it in helium-6, and using some plastic in order to normalize the beam, and using MUS2 telescope to identify particles, like where here you have the identification matrices, delta E, where I color the helium-3 part and the proton part. But also we use MUS2 as a kinematic for kinematic reconstruction via missing mass. I can also present you some preliminary results about this setup. And here I benchmarked this setup on another reaction, on helium-6p triton alpha reactions, where you can see here the kinematic plot with IJCLab energy laboratory and angle laboratory, where you can see the kinematic line of a triton, of the kinematic of the triton in coincidence with an alpha. Of course, we can reconstruct the excitation energy in the alpha energy system, where you can see that there is a tiny bump. So of course we can zoom in a bit to see, in fact, the peak of the ground state of the alpha particle. Here, yes, of course, there is still some alignment to do because the analysis is still ongoing. About the helium-6 and helium-3, here I present you the same kinematic plot with the IJCLab Tetra-Lab for at least a coincidence with helium-3, and here with in coincidence with proton, deuteron, and triton. I can show you also the kinematic line that we are expected for hydrogen 4. So in the black, it's the lowest ground state resonance, and in red is the highest ground state resonance. And basically in purple, we have the expected EIS resonance. Performing the excitation energy, we can have the energy in the system of hydrogen 4. And of course, we can see for each coincidence case with triton, deuteron, and protons, the related energy, excitation energy. So here in green is for the triton, where we can see that there is potentially the ground state resonances of the hydrogen 4. And for the other one, we start to see in deuteron potentially a bump in deuterons, and we really need for this, in fact, for the proton coincidence and deuteron coincidence, evaluate the background in order to be sure how much and how it can be reliable in this region about more events in this region, in order to know if, well or not, there is some EIS in these regions. Of course, there is still work to do, and the ongoing work and the next work to do is the phi correlation. What we detect, and in fact we detect that particles are strongly correlated as a back-to-back emission, where here you have the correlation matricing between telescope, where if for multiplicity 2, you detect a proton in the first telescope, where is detected the helium-3, and we see the pairs T1, T3, and T42, that is in fact the diagonal telescope and implies a back-to-back emission. So this is the next step for phi correlation. But also, as I mentioned before, we really need to know how much is the background, and we have to evaluate the background in order to determine if there is or not an EIS in the region of interest. And so a huge development of n-body phase space calculation is ongoing in order to estimate the background. So here I have the 3 examples for our reaction, where here you have the evaluated phase space for the emission in the hydrogen for P3 plus 3N, the D plus 2N, but also the T plus N. That slide concludes my webinar. So if you have some questions, I'm here, and thank you for your attentions.